In this lesson, we are going to be looking at what do samples tell us about data. So you'll notice here, we still have our definition of population and sample, which population is the whole group we want to know about. Sample is just the group we survey, we actually collect the data from. What goes along with that is called a parameter and a statistic. The parameter is about the population, the statistic tells us about the sample. So to remember that, the P and S kind of go together. The symbol that we use for parameter is P, so that's from our population. The symbol we use for statistic is P hat, and that's literally what it's called, is P hat. Anytime you see this hat on a variable, that tells you it comes from a sample. Any hat, with anything you deal with future variables you'll learn about, when you see that hat there, it's not true data, it's from a sample. So it's from the people you surveyed or asked or questioned or whatever you did with them. So a parameter, it says, what do we want to find out about the population, or what do we already know to be true about the population? Sometimes if you did a census, you might already know something about the population. What our sample statistic then is what we find out about a population by conducting a study. So this is what we're going to actually do with our survey. Our parameter is fixed. It never changes. If 75% of Americans in the last 2012 presidential election voted, it's going to stay 75% 5 years from now. No matter when that happened, every election, history books, our children's children will go back and they will study that 75% of people voted in the 2012 election. Now, a statistic can change from sample to sample, and we'll talk about that in just a minute. I'm going to show you an example of that. So here in this example it says 20% of Americans are obese. That's given to us. We're told that. They did a census and they found that out. A survey was taken of everyone who went to the doctor last week, and 25% were obese. Are these numbers parameters or statistics? So my parameter is this one right here. The 20% of Americans are obese. That's my parameter. I'm told that. That's coming from somewhere. In just the people who went to the doctor last week, 25% were obese. This is my statistic. It's just out of the people that went to the doctor last week. So that's how we would define those. Do samples always give good data about the population? So here, when we read this one, it says, suppose that in fact, unknown to Gallup, Gallup is the major company who does all the surveying for our country. There's a lot of Gallup polls you'll read about. Exactly 60% of all adults have bought a lottery ticket in the past 12 months. Since Gallup didn't know that fact, so the parameter is 0.6, that's our 60, they conducted 2 studies to determine the number of adults that have bought a lottery ticket in the last 12 months. So they did 2 statistics. They did a survey. And here's what they found. They did a simple random sample, that's what this SRS means, of 100 people. So the N is the number of people they surveyed. They surveyed 100 people. In the first survey, they found that 56% bought lottery tickets. In this simple random sample of 100 people, they found 46%, and in this simple random sample, they found 61%. So notice, every sample they took, they got a different answer. Their P hat is different for every sample, and it really should be, because it's a random sample. You don't know what you're going to get. Now the population, when they looked back on the data later, and they actually could tell who bought lottery tickets, how many people, it turned out the parameter here is 60%. What happens in a smaller sample, so their sample is 100 people, they have some at 45%, some all the way up to 70%, but notice this normal curve. There's a normal curve here. Okay, look at that actual population. There's quite a few people here. That's where the most happened, because that's really where the data lied. So over many samples, they got closer to the population. Take a look here now. When they did a simple random sample of 1,523 people, look at their numbers. The more people they sampled, the closer they were to the actual population. Do you see that? So that if we want to get a better statistic, so it's closer to the actual data, what we need to do is increase our sampling size. So the more people you survey, the better your results. Look at their results right here. This data has a much smaller standard deviation. Look at our other picture. See how that data is really spread out? It's very spread out because my sample was so small. So I had some results at 45% and some at 70%. There's a big range in those scores. I have a high standard deviation for that graph. It's normal, but I have a high standard deviation. Now look at this other graph where they took a higher sample size. So they went from 100 to 1500. They times it by 15 almost. A little bit more, right? There's no one below 0.55 and no one above 0.65. Their data is really conclusive. Very, very small standard deviation. So this data is better, right? The samples were closer to the actual population. The more people we survey, the closer we'll get to that. So as they keep surveying, one of the things that's called the law of large numbers. So law of large numbers, I think we've talked about this before. The law of large numbers tells us the more times we do a survey, or the more times you flip a coin, we talked about it, I think, with probability. The more times we do something, the closer we'll get to the actual value if we survey a lot of people. So that's why when you're doing a simple random sample, you have to decide how many people to survey based on your population, because it matters. If I only survey 5 kids in our school, it's not a representative sample, right? I'm not going to get good results. If I survey 300 kids out of the 1,000 in our school, maybe I'm going to be more likely to get some good results. So with this now, when I do the survey, there's something called the margin of error, which you'll see on TV when you're looking at surveys. It comes up a lot when they're doing presidential elections or any kind of elections. They'll say, you know, so-and-so is leading by 10 percentage points. Margin of error is plus or minus 3%. So what they mean by that is if they say, let's say, we'll say, since President Obama just won the election, we'll say President Obama was leading by 10%, and they'll say plus or minus 3%. That means they believe he's leading by anywhere from 7 to 13%. We subtract 3 and we add 3 to that percentage. Now, the margin of error, to find it, we would take 1 divided by the square root of n. Remember, n is the number of people surveyed. And then we round it to the nearest percent. N is the sample size. Oh, sorry, it's right there. And this is for a 95% confidence level. There are different confidence levels. 95 is the most common, so that's the one we're going to talk about. If you move on to AP statistics, we talk about a 99% confidence level and a 90% quite a bit. But 95 is the most popular all the way through, no matter what you're studying. So MOE is margin of error, that's just the abbreviation, is rounded to the nearest percent. To decrease, this is a big deal. This was on your MCA, I think, this year, people told me. To decrease the margin of error, you take a bigger sample. Doesn't that make sense? We just saw that in the graph. The more people we surveyed, the closer we were to the actual population. So we make our standard deviation decrease, which makes our results more reliable, right? There's not as much spread. And so the more people we survey, the lower our margin of error would be. This is really important. Your margin of error is determined by your sample size, not your population size. So if I am surveying just students in my Block 1 class, or I'm surveying the whole school, I don't have a different margin of error because there's different populations there. My Block 1 class has 30 kids in it. The whole school has 1,200, let's say. There's a big difference there. But if I do a sample of 5 kids here and a sample of 5 kids here, my margin of error would be the same, which is crazy to think about, right? But that's how it works out. It's based on your sample size. So we're going to calculate the margin of error for all these different sample sizes. We have a table here. For each one, you take 1 divided by the square root of n. So 1 divided by 100, which hopefully we know is 0.1, right? So we'd get 0.1, and then we times that by 100 to make it a percent. So we'll move that to 10%. So we'll get the decimal, and then you make it a percent in the next column. Here we'd have 1 divided by the square root of 200, which gives me 0.0707. And when I make that a decimal, or excuse me, when I make that a percent from a decimal, that's 7%. We round to the nearest percent. 1 divided by square root of 400, I get 0.05, 5%. 1 divided by the square root of 1600, I get 0.025, which makes it 2.5%, right? This would be 2.5%. Round to the nearest decimal, though, or nearest percent, excuse me, that'd be 3%. Last one, if I have a sample of 2,500, I get the decimal of 0.02, which is 2%. So, notice what's happening as I am increasing my sample size. So I started with 100, I go all the way to 2,500. Look at what's happening to my margin of error. Increasing your sample size decreases your margin of error. So ideally, I would survey 2,500 people, wouldn't I? And I only have a 2% margin of error. How do you cut your margin of error in half? Look at that question. Well, let's see. Did any of these cut in half? Yeah, we had some cut in half. Let's look right here. From 10% to 5%. That cut it in half, didn't it? What did I do to my margin of error to make that happen? Well, I went from 100 to 400. So this is a sample size of 100. This is a sample size of 400. So it looks like I took it times 4. So to cut a margin of error in half, we quadruple the sample size. So times by 4. Now some of you might have been thinking that maybe you just times it by 2 because you're cutting it in half. But remember in the formula there's that square root. What's the square root of 4? 2. So we are cutting it in half. Think about this. The square root of 4 is the same as 1/2. So there's quadrupling my sample size. So then how do you do a margin of error cutting it in third? You're going to take it times 9. So take 9 times and do a bigger sample. So 3 squared is 9, 2 squared is 4. See the pattern here? So then how do you do it to the fourth? Well, what's 4 squared? So take it times 16. So if they ask you how to do it times, how do you cut a margin of error of fifth in fifths? To cut it in fifths, you take 5 squared, so you take it 25 times bigger. So if they ask you to cut your margin of error ever, you'd have to take a much bigger sample, wouldn't you? And the more they want you to cut it, the bigger the sample would be. Here it says the margin of error plus or minus, this is kind of what I explained before. If we took many samples, so this is a formal definition, this is a big deal, and if you're taking AP Stats, we talk about this a lot. A margin of error of plus or minus 3 means if we took many samples using the same method we used to get this one sample, 95% of the samples would give a result within plus or minus 3 percentage points of the actual truth about the entire population. Right here, if you knew this, this is one AP question on the AP test probably. So, what that really means, because that's a bunch of words that don't really make sense. If I was going to survey our school, and let's say I put everyone's name in a hat and I drew out 100 kids. Well, actually, let's go back. 3% was what? How many kids would I survey? 1,600 kids. So let's say I'm in a big school. So let's pick a school that's got a population of like 3,000. So that can happen because we don't even have 1,600. I survey 1,600 students, and I ask them, do you plan to go to college? And in my first sample of 1,600, I get, let's say, 75% of kids say yes to that. And in my second sample of 1,600, I get 73%. And in my third sample of 1,600, I get 81%. Now, over time, I expect 95% of my samples to be within my thing. So my sample, let's say right here, here's my sample. I would say this one gave me 75% and I'm at it plus or minus 3%, right? That's what 1,600 is, 3% margin of error. So I expect my kids to be between 72 and 78%. 95% of the time when I survey the same school over and over, I expect 95% of the time my students to land between 72 and 78% for wanting to go to college. Look at what happened. It happened here, didn't happen there. So that'd be like my 1-5% weirdness, right? But if I kept doing this, most of them would be in there. So I did it again, I got 77%. I did it again, and I got 73% again. So that's what that's saying. 95% of the time, when we do the same survey the exact same way, we draw the names out of a hat, we didn't change any of the students, it's all the same, I'm going to get results in that range. 95% of the time, which is pretty reliable, right? Here's an example. If you do one survey and sample 500 people in the population of 2,500 people versus another survey where you sample 500 people in a population of 10,000 people, which survey has a larger margin of error? This is to trick you because we talked about how no matter how much is in the population, whatever your sample size dictates your margin of error. These are the same sample size, so they have the same margin of error. So same MOE for both. If you were to calculate that, you'd have to take 1 divided by the square root of 500, and then times it by 100 to get that decimal. But they didn't ask us to do that, so here's my answer. Same margin of error for both. Now, confidence statements. A confidence statement tells you the level of confidence that you feel. So I'm 95% confident that this is going to happen. 95% is the most common, but again, there are 90% and 99% would be the second most common. And then they include the parameters, so who we're talking about, and then what we found out about the people we surveyed, and our margin of error. A bigger confidence level means a higher margin of error. So if I'm 99% confident, that margin of error is greater than me being 90% confident, the margin of error for that. So the more confidence I have, the higher margin of error I have. More chance for errors because I'm more confident. So, confidence statements examples. We are 95% confident that the percent of teenagers that approve of gambling is 52% plus or minus 5%. So that's in the range of 47 to 57%. We are 95% confident that the percent of teenagers that approve of gambling, so apparently my population was teenagers who approve of gambling, right? That was my question I asked them, and I gave you what I found. So that's a confidence statement. Here's our example. I feel like I missed something here. Maybe not. Okay. Here's an example, and we're going to list what they're talking about here. A recent study was done by the Mayo Clinic. They wanted to find out how many females between the ages of 18 to 28 exercise 3 times a week. They gave a written survey to 300 randomly selected females between the ages of 18 and 28 and found that 123 exercised 3 or more times a week. So, population, who or what are we choosing from? So we are choosing females, right? Aged 18 to 28. No one else are we talking about. Just females ages 18 to 28. What do we want to find out? We want to find out that if they exercise 3 times a week. Sample. How many people are being chosen? So our sample was 300 randomly selected females aged 18 to 28. And then our statistic. So that's actually what we found out. Of those 300 females, we found 123 want to exercise 3 times a week. So 123 out of 300. We're going to use that actual data. So 41% exercised 3 times a week. So that's just of our sample. That's not all females, that's just our sample. Our margin of error, so we'll use the formula. We surveyed 300 people, so we take 1 divided by the square root of 300. So we get 0.0578, and when I round that to the nearest percent, our margin of error is 6%. So our confidence statement would say, we are 95% confident that the percent of females age 18 to 28 that our parameter, so what we're looking for, that exercise 3 times a week is, and we found it to be 41%, plus or minus 6%. So then we'll put the range in the bottom, so I'll subtract 6 from 41 and I'll get 35. So it's 35 to 47%. That's what you're going to fill in every time you're doing a confidence statement. We are 95% confident that the percent of females aged 18 to 28 that exercise 3 times a week is 41% with a margin of error of 6%. So that's what we would report when we're doing that. Now we're going to continue to work with stuff like this, but to start you're going to kind of get the hang of it by doing a worksheet tomorrow and a couple of objectives, or just, excuse me, one objective. And this is actually going to be 54, that's a typo. And if you have any questions on this, make sure you let me know tomorrow.